In section 10.4, we're adding and subtracting and multiplying radical expressions. Add or subtract as indicated and assume that all variables represent positive real numbers. Now the thing to remember about adding or subtracting radicals is that the radicals must have the same index and the same radicand. In example A, we have the square root of 63 minus the square root of 7. We can't simplify that as written, but we can simplify the square root of 63. The square root of 63 can be written as 9 times 7 is 63 minus the square root of 7, and the square root of 9 is 3, so we can bring that out in front of the radical with the 7 left under the radical. So the square root of 63 is the same thing as 3 times the square root of 7. And we're going to subtract the square root of 7 from it. So we have 3 radical 7 minus 1 radical 7, and our answer is going to be 2 radical 7. So we can only add or subtract radicals if they have the same index and the same radicand. We simplified square root of 63 so that we ended up with a 7 under each radical sign. In example B, we have negative 3 times the square root of 200 minus 5 times the square root of 8 plus 9 times the square root of 98. We can't add those radicals together yet unless we can simplify and end up with like terms. We can write the square root of 200 as 100 times 2. And 100 is a perfect square, so the square root of 100 is 10. So this can be written as negative 3 times 10 times the square root of 2. And then negative 3 times 10 is negative 30 times the square root of 2. And now let's simplify the minus 5 times the square root of 8. Well, the square root of 8 can be written as 4 times 2. And the square root of 4 is 2, so we can bring that out in front. So it becomes negative 5 times 2 times the square root of 2, or minus 10 times the square root of 2. And then with this 9 times the square root of 98, we can write this as factoring 98 into 49 times 2, where 49 is a perfect square, and the square root of 49 is 7, so we can bring out 9 times 7 in front of the radical and leave the 2. So that'll give us 63 radical 2. Now we can combine like terms here. We have negative 30 square root of 2 minus 10 square root of 2. Those are like terms, so we could write this as negative 40 square root of 2 plus 63 square root of 2. These are like terms, so we can combine those to get negative 40 plus 63, or 23 square root of 2 as our final answer. Let's simplify D, the cubed root of 8x minus the cubed root of 27x. We can't simplify these unless we have the same radical, same index, same radicand. But each one of those can be simplified. The cubed root of 8 is 2, so we can take out that perfect cube in front and leave the cubed root of x underneath the radical. 27 is a perfect cube as well. 3 to the third is 27, so we can write this as minus 3 times the cubed root of x. Now we do have like terms. Our like terms are the cubed root of x, so we have 2 cubed roots of x minus 3 cubed roots of x, and that will simplify to a negative 1 cubed root of x, or we can write it simply as a negative cubed root of x as our final answer. In example E, can't combine these unless we have the same radicand, and these are certainly different, but we can simplify each one first. Let's leave that 7 in front of the cubed root, so it's going to be 7 times the cubed root of x to the third. X to the third is a perfect cube, so we're going to be able to simplify that out. Y to the 13th is not a perfect cube, but y to the 12th is. So y to the 13th we can write as y to the 12th times y, or y to the first. And these two are going to be perfect cubes that we'll be able to bring out in front. Plus, we have 5xy out in front, and we have the cubed root of 8. 8 is a perfect cube, so we'll be able to simplify that. Y to the 10th is not a perfect cube, but y to the 9th is. So we can bring out a y to the 9th and leave a y underneath the cubed root sign. Now let's simplify this. We're going to be able to take the x cubed and y to the 12th out. So we're going to have 7, and that cubed root of y is going to be left under there. But when we take out the cubed root of x cubed, that's x, and the cubed root of y to the 12th is y to the 4th. Plus this 5xy, and we're going to take out 8, which is a perfect cube, and y to the 9th, which is a perfect cube. And then the only thing that will be left is that cubed root of y. So when we take out the cubed root of 8, that is 2, and the cubed root of y to the 9th is y to the 3rd. So let's simplify this. We have 7xy to the 4th times the cubed root of y as our first term. And our second term, when we simplify this, 5 times 2 is 10x y to the 4th times the cubed root of y. That's our second term. Now we can combine these only if we have like terms. The like terms should have the same radical, same radicand, and also the same variables out in front. Xy to the 4th cubed root of y, xy to the 4th cubed root of y. That is the like terms. So we add the coefficients together to get 7 of those plus 10 of those, or 17 xy to the 4th times the cubed root of y as our final answer. Let's simplify example G, where we have 2x square root of 11 over 5 plus the square root of the fraction 11x squared over 100. The first term is simplified, so we're going to leave that alone, 2x square root of 11 over 5. But the second term will split up so that we have the square root of 11x squared in the numerator and the square root of 100 in the denominator. Again, that first term we're going to leave alone for now. That second term can be simplified. The square root of 11 is not a perfect square, so we're going to leave that square root of 11 alone. But the x squared is a perfect square. Square root of x squared is x, so that x is going to come out in front. And in the denominator, the square root of 100 is 10. Now we have two fractions, and we can add fractions together if we have a common denominator. So that LCD would be 10. We would need to multiply the numerator and the bottom, numerator and denominator, by 2 in order to get a common denominator of 10 so that we could add the numerators together. When we do that, we get 4x square root of 11 over 10 plus x square root of 11 over 10. Now we can add the numerators together, 4x square root of 11 plus x square root of 11 all over 10. We're getting there. 4x squared of 11 plus x squared of 11. These are like terms, so we have 4 of them plus 1 more of them will give us 5x square root of 11 over 10. Now the 5 and the 10, you can simplify that just one step further to get x squared of 11 over 2 as our final answer. Let's simplify h so we can determine if we can combine like terms. 10 times the 4th root of x to the 7th we can write as 10 times, we want to take out perfect 4th powers. So x to the 7th is not a perfect 4th power, but we can split it up into x to the 4th times x to the 3rd. The second term we can't simplify any further. We write it as 2x times the 4th root of x to the 3rd. Now since we're taking the 4th root of x to the 4th, that's a perfect 4th power, we can take that out in front, and that's going to give us 10x out in front of the 4th root of x to the 3rd power, minus 2x times the 4th root of x to the 3rd power. So we have like terms here. They both have x times the 4th root of x to the 3rd, x times the 4th root of x to the 3rd. So these are like terms, so we can combine the coefficients. 10 of those minus 2 of those is going to get 8x times the 4th root of x to the 3rd as our final answer. For these examples, we are going to multiply, then simplify if possible. Assume that all variables represent positive real numbers. We'll use the distributive property to distribute the square root of 6 times the quantity square root of 5 plus the square root of 7. When we use the distributive property here, we get the square root of 6 times the square root of 5 is the same thing as the square root of 6 times 5. And then the square root of 6 times the square root of 7 is the square root of 6 times 7. So this we can write as the square root of 30 plus the square root of 42. Now neither of those can be simplified, so our final answer is the square root of 30 plus the square root of 42. We cannot combine those because they're not like terms. Let's do the same thing for B. We're distributing the square root of 7 to the quantity square root of 11 plus the square root of 7. When we multiply, we get the square root of 7 times 11 plus the square root of 7 times 7. And that gives us the square root of 77 plus the square root of 49. Well, the square root of 77 cannot be simplified, so we're going to leave it as the square root of 77. But the square root of 49 can simplify to simply 7. So we have as our final answer the square root of 77 plus 7. In example C, we want to square the entire quantity. So we can think of it as multiplying a binomial times a binomial, the square root of 7 minus the square root of 2 times the square root of 7 minus the square root of 2. And then we can use first, outer, inner, last, where the first is the square root of 7 times the square root of 7, which is the square root of 49. That's our first. Our outer is the square root of 7 times the square root of 2 with a negative, so it's going to be minus the square root of 14. The inner is negative square root of 2 times the square root of 7, which is minus the square root of 14. And this last is negative square root of 2 times negative square root of 2, which is going to be a positive square root of 4. So we can simplify and combine like terms here. And we get the square root of 49 is 7. And we have minus 1 square root of 14 minus another square root of 14, so we can write it as minus 2 square root of 14. And plus the square root of 4 is the same thing as plus 2. Now we can combine the constants as like terms to get 9 minus 2 times the square root of 14 as our final answer. Let's multiply the square root of 2x times the quantity square root of 2 minus the square root of x. Using the distributive property, we get the square root of 2x times 2, which is the square root of 4x, minus the square root of 2x times x is 2x squared. We can simplify the first radical for x as 2 times the square root of x, since 4 is a perfect square, but x is not, that stays under the radical, minus, well, this x squared is a perfect square, so we can bring an x out in front, but that 2 is not a perfect square. We leave that under the radical. So our final answer is 2 radical x minus x radical 2. In example E, we're going to use the FOIL method to multiply the binomials with radicals in them. So we'll use the first, outer, inner, last. Since we're multiplying a binomial times a binomial. When we multiply the first, we can multiply 6 and 3 together to get 18, and radical y times radical y is radical y squared, which we'll be able to simplify in the next step. The outer is 6 square root of y minus 1, so it's going to be minus 6 square root of y. Then we have the inner, z times 3 square root of y is a plus 3z square root of y. And then finally our last is z times negative 1 or minus z. Let's simplify the first term to get 18y. Now none of the other terms can be simplified. 6 square root of y plus 3z square root of y minus z. So we can't combine any other like terms. In order to have like terms, you must have the same variables, the same index, the same radical, and the same radicand. And none of those are like terms, so our final answer is 18y minus 6 radical y plus 3z radical y minus z. In example G, we're multiplying the binomials with radicals. We can use the FOIL method, using the first, outer, inner, last. When we multiply the first, 5 square root of 3 times 6 square root of 3, we can multiply the 5 times 6 together to get 30, and the square root of 3 times the square root of 3 to get the square root of 9. The outer is 5 square root of 3 times negative 4, so that gives us minus 20 square root of 3. Then the inner is 9 times 6 square root of 3, which is 54 square root of 3. And then the last is 9 times negative 4, which is negative 36. We can simplify the first term because we know square root of 9 is 3. So it's 30 times 3, or 90, minus, and these two terms are like terms, so we can combine those to get a negative 20 square root of 3 plus 54 square root of 3 is a plus 34 square root of 3. And then minus 36. We're going to combine the constants to get 90 minus 36, or 54 plus 34 square root of 3 as our final answer. In example H, we're multiplying the entire binomial, so you can write it as the square root of x minus 4 plus 3 times the quantity, the square root of x minus 4 plus 3. Using the first, outer, inner, last, where our first is the square root of x minus 4 times the square root of x minus 4, and that is going to be the square root of x minus 4, that quantity squared, which is a perfect square. We'll be able to simplify in the next step. The outer is x square root of x minus 4 times 3, so it's going to be plus 3 times the square root of x minus 4. The inner is 3 times the square root of x minus 4, so it's going to be plus 3 times the square root of x minus 4, and then the last is 3 times 3, which is plus 9. Now the first term can be simplified because it's the square root of x minus 4 squared, so that simplifies to just x minus 4. The middle two terms are like terms, so we have 3 square root of x minus 4 plus 3 square root of x minus 4 like terms, so it's going to give us plus 6 square root of x minus 4 plus 9, and we're nearly there. We can add these two constants together that are like terms to get x plus 5 plus 6 square root of x minus 4 as our final answer.